Moist adiabatic motion. A warning, there's a little bit of maths in this video, so if any time you need to stop and step through it carefully, feel free to do so. We've already examined the concept of dry adiabatic motion. That is, if I have a parcel of air that contains no moisture in it at all, if I lift it up, at what rate will it cool? Now we're going to consider the case where a parcel of air contains water vapor, but it's unsaturated. So it's moist adiabatic motion. In other words, we're going to make some assumptions about the fact that the parcel doesn't exchange heat with its environment, but it contains water vapor. The specific heat of water vapor at constant pressure, CPV, is 1878 joules per kilogram per Kelvin. So let's apply the first law for moist air. So what do we have? Del Q is equal to m Cp dt. So we're going to have in other words, what we're trying to do is derive what Cp is for moist air. So the mass is equal to the mass of dry air plus mass of vapor. So that's the second expression there. But that's also going to be equal to the delta Q's that go into the dry air and the vapor. So the delta Q for the dry air is md Cpd by dt, and for the vapor, mv Cpv by dt. So if we equate both sides of that equation, the dt's cancel, and we can divide through by the total mass, md plus mv. So Cp for moist air is equal to md on md plus mv by Cpd, plus mv, the mass of the vapor, divided through by the total mass, multiplied by Cpv. Now we've earlier seen the specific humidity, Qv, is equal to the mass of vapor on the total mass of the air. And it's straightforward to show, and I'll leave that as an exercise for you, that md on md plus mv is 1 minus Qv. And so we have a more simplified expression that Cp, the specific heat of the moist air, is equal to 1 minus Qv by Cpd plus Qv by Cpv. You can see straight away as Qv goes to 0, that is, our parcel becomes dry, then Cp is equal to Cpd, the dry gas specific heat. We can rearrange that equation just slightly as shown there, so that it's entirely in terms of Cpd. So we take out a factor of Cpd, and it gives you the expression shown there, including the ratio of Cpv to Cpd. Now we can work out what that ratio is because we know Cpv and Cpd, and so you end up with the approximation that Cp, the specific heat of moist air, is equal to Cpd outside of 1 plus 0.87 Qv, the specific humidity. A little bit messy. Now let's consider the potential temperature of moist unsaturated air, theta subscript u. So if no liquid water is present and no phase changes of water take place, our original derivation of potential temperature arising from an adiabatic process is the same as for dry air, just with different constants. In other words, we can use the same Poisson's equation. Theta u is equal to T multiplied by P naught on P R to the Cp. But now the values R over Cp are not the dry values, they're the moist values. And we won't show it here, but R is approximately equal to Rd, 1 plus 0.608 Qv, and as we've shown just before, Cp is approximately equal to Cpd, 1 plus 0.87 Qv. So what we can do then is substitute those in our equation for our unsaturated moist adiabat, and that's shown in the top equation there. Because Qv is typically small, we can do a Taylor expansion of the denominator, and because Qv is small, we will ignore terms involving Q squared and larger because they'll be very small compared to 1. That will leave you with a quadratic, which is 1 plus 0.608 Qv multiplied by 1 minus 0.87 Qv. And when you multiply that out and you ignore factors involving Qv squared, you end up with the approximate expression shown below, where theta u is T multiplied by P naught on P to the RD on CPD multiplied by 1 minus 0.26 QV, which is all a bit of a mouthful. Now, as we've said already, QV is typically very small. It's often less than 0.03, and so consequently the power which we raise P0 and P2 is approximately equal to RD on CPD, which is another way of saying that unsaturated moist adiabats can be approximated to a high degree of precision with dry adiabats, and they vary by as little as 0.1 degrees Celsius. And what this means is that on an aerological diagram like a skew T log P or F160, we can approximate both dry adiabatic motion and unsaturated moist adiabatic motion using the same dry adiabats.